Dear students and participants of the course on railway engineering, today we are going to look at some numericals related to hauling capacity and resistances. In the previous lecture, we already talked about hauling capacity, where we have defined it as the multiplication of the coefficient of friction with the number of driving wheels and the load which is coming on a driving wheel, or in other form we can say it has also be taken as total load which will be there on a train. The another thing which we discussed was a tractive effort. In the case of tractive effort, along with the various factors, we did talk about the effort for steam engines, diesel locomotives and the electric locomotives. Now, today we will be looking at the various numericals related to the hauling capacity and the resistances being offered by a track. Let us start with the first numerical. What is the information which is being given to us? There is a locomotive with an axle load of driving wheels of 22 tons and there are 3 pairs of driving wheels. That means this is a small w and this is n, and it is moving on a broad gauge track. The speed of the train on the straight level track is 80 kilometers per hour, that is capital V is being given to us. Coefficient of friction is 0.2, so that means this is small f. What we have to calculate? We have to calculate the maximum train load that this locomotive can move on this track. So, the very first thing which we have to do is to calculate the hauling capacity, because what we are going to look at is the hauling capacity has to be at least equals to the various resistances being offered by the track, or otherwise it should be more than that. The hauling power of this locomotive or capacity is being defined as the multiplication of F, N and W. So, this F, N and W, if we put the values here, F was 0.2, the W is 22 and the number of driving wheel pairs is 3. So, what we get is 13.2 tons. Now, what are the resistances which have been offered on a straight track? So, there is no curvature, there is no gradient effect. So, it means the initial values are going to be there which are related with the resistances which are dependent on speed or which are not dependent on speed and the atmospheric condition. So, that means we have due to friction, due to wave action and due to wind, these resistances will be there, and we put these resistances, the values are 0.0016 into W plus 0.4 times 0.8 into W into V plus 6 times 0.6 into W into V square. So, this is the formula which will be there here. So, this is one of the simpler formula. Not many things are being there because those are not being given in your numerical. Now, W is a common attribute here. So, say we can even take the W out. So, this is the formula. Here we are putting the value of V, which is the speed 80 kilometers per hour here. So, we get this value. So, when we put all these values, what we get is 0.01184 W. Now, 0.01184 W is the total resistance and the hauling power is known to us. So, we have this hauling power and we have this rolling total resistance. So, now we are going to equate these two SC and RT. Now, when we equate these, then we get 13.2 is equals to 0.0118 W. So, this gives us a load of 1115 tons. It means for the given conditions, the locomotive which was having 3 driving pairs and which was having axle load of 22 tons on each of the driving wheel, then that is going to take the load of 1115 tons as a total of the total train. That means it includes the load of the locomotive, it includes the loads of the wagons. Now, let us move to the next numerical here. Now, in this case again we have been given that 22 tons are coming on one of the driving wheels axle combination and there are 3 such pairs. So, that is defining our condition for hauling capacity. Then this train is having a weight of 1115 tons. So, the total weight is now given to you, and this is moving on a broad gauge track. The speed of the train on a straight level track is 80 kilometers per hour. So, this is 80 kilometers per hour V. The coefficient of friction F is given as 0.20. Now, what we have to calculate? We have to calculate the speed of the train. If it is going to move on a track with a rising gradient of 1 in 200, that means the G value has been given to us now. So, some of the conditions remain the same as we have talked in the case of a straight level track previously, the three of the formula which have been used. Now, one which is going to be added is for the gradient effect. So, let us solve this. So, very first thing again remains the same. So, first of all we are going to calculate the hauling power of the locomotive, which is N into W into F, and then we are going to check it with respect to the resistances offered by the track, where the resistances now are being defined additionally with the gradient also. So, the hauling power of the locomotive when we look at, so N is the number of driving wheels which is given as 3, 22 is the axle load coming on each of the driving wheel axle combination, and the coefficient of friction is 0.2. So, that gives you 13.2 tons as the hauling power. So, this is one value which finally we are going to equate. Now, let us write down the various types of resistances which will be there. The resistances are there due to the rolling frictions, due to the wave actions, due to the atmospheric wind when we are saying that it is not blowing. So, there is no velocity of that wind, and then due to the gradient. So, the first three formula which will be here are the same as we have discussed in the previous numerical also. So, there also we said it is 0.0016 W, 0.00008 W into V, then 0.0000006 into W into V square plus W into tan theta, or we can also write this as W into G, where G can be a percent value. So, when we place the values here, we have been given the value of W as 1115. You can see that it is being given as 1115 already. So, when we put that value here, so what we get is 0.00016 into 1115 plus 0.00008 into 1115 into V plus 0.0000006 into 1115 into V square plus 1115 multiplied by 1 by 200, which is the gradient. Now, when we have all of these values, some of the values are with V and some of the values are in terms of a constant. So, what we get here is this particular equation 1.784 plus a constant with V and a constant with V square plus again a constant value of 5.575. So, it all together comes out to be 7.359 plus an equation in V, and if we equate it with the hauling capacity, then in that case hauling capacity it comes out to be 13.2 is equals to the equation given here. Now, what is left here is to solve this equation for V. So, it is a quadratic equation, you can very easily solve this particular equation. On solving this equation, the value comes out to be 48 kilometers per hour. So, the speed on the gradient is going to be 48 kilometers per hour. If I compare this with respect to the previous numerical, the only information which has changed is the gradient. So, in the previous numerical the value was 80 kilometers per hour. So, if a train was moving at a speed of 80 kilometers per hour, but when we have gone to a gradient it has reduced to 48 kilometers per hour for the same conditions being given. That means there is a big reduction. So, there is a reduction of 32 kilometers per hour here. So, the gradient has created a lot of difference, and that is where in the previous numerical which we did talk towards the end of the previous lecture, there also we have seen that we were expecting to have this train moving at a speed of 50 kilometers per hour, but because we found that the hauling capacity was not available, it was less than the resistances which was offered by the gradient, the train was not able to move at a speed of 50 kilometers per hour. Now, the next numerical which we can see here, again the conditions are given the same, that means 22 tons which are coming on a driving wheel axle combination. There are 3 pairs of driving wheel axle combinations, and there is a weight of the train which again is 1115 tons. So, we have small w, we have n, we have capital W being given there, and the speed of the train on the straight level track is 80 kilometers per hour. So, this is a capital V. Coefficient of friction F is 0.2. So, the values are being given to you. Now, what is being added? We have to calculate the speed of the train if it moves on a track with rising gradient of 1 in 200, and this gradient was same in the previous numerical, but this is an addition. The curve of 4 degrees has been also attached. So, we are going up as well as there is a curvature here. The process remains the same for the solving of all of these numericals. The very first thing, we are going to equate what the hauling power and the resistances. So, if we understand that, it means the very first thing which we need to calculate is the hauling power, and this is nothing, this is N into W into F. So, if we put the values for N into W into F here, what we get is 13.2 tons. Now, the next thing which is to be calculated is the resistances. Now, resistances here are going to be with respect to friction, with respect to wave action, with respect to wind, with respect to gradient, and with respect to curvature. Now, this is added here. So, when this is being added, it means for a broad gauge, it is 0.0004 W into dr, where dr is the degree of curvature. If it would have been a meter gauge, then this 4 would be 3, and then narrow gauge it will be 2. So, now we are going to place the values here. Now, when we put the values here, V we have to calculate. So, in this case, W is already there, tan theta is known to us, dr is known to us. So, let us put all of these values in the equation, and when we put this value in the equation, what we get is 1115 into 0.0082 plus 0.00008 V plus 0.000006 V square. And when this is being equated with the hauling capacity or the power 13.2, then what we have is a quadratic equation being given here. Now, if we solve this quadratic equation, we are getting a value of 43 kilometers per hour. So, that means now the speed has further gone down. Previously it was 48, but the effect of curvature is not that tremendous. It has made an impact of only around 5 kilometers per hour. Now, let us move to another numerical. Here there is a locomotive where the load on the driving wheel is now 24 tons, and it has 4 pairs of driving wheels, and they are moving with a train weighing 1200 tons on a broad gauge track. The speed of the train on the track with gradient 1 in n is 60 kilometers per hour. The coefficient of friction is 0.20. We have to find out what is this maximum gradient on which the train can move at a speed of 60 kilometers per hour. So, with the same concept, first of all, let us calculate the hauling power of the locomotive by using the formula N into W into F. So, here when you go with this formula N into W into F, then this is N is given this time as 4, W has changed, it has been given as 24, F has remained same as 0.2. So, the overall value instead of 13.2 has changed to 19.2 tons. So, the hauling power of the locomotive has increased here. Now, let us look at the resistances which have been offered. So, resistances which are offered are due to friction, due to wave action, due to wind, and due to gradient. So, the first 3 are going to remain the same, that is 0.0016 W, 0.00008 W into V plus 0.0000006 W into V square. And what we add is W into tan theta, or as I said previously also W into G. This is the value which we can add here. If we add them and we put the values, so W is 1200 being given to us, and the speed is being given as 60 kilometers per hour, but we have to identify this value of 1 in n, that is G. So, when we go with this particular equation and we equate this equation finally with the hauling capacity, so what we get? So, the resistance comes out to be 10.272 plus 1200 into G %. Hauling power is being given as 19.2, or it is being calculated actually, and this is being equated here. So, when you equate them, you get a value of G as 0.00744, or we can say as 0.744%, and when you convert it into 1 in n, then it comes out to be 1 in 135. So, this is the gradient which can be traversed. So, we are saying that if you go here, this is 1, this is 1 in 135, then the train which is moving here can move at a speed of 60 kilometers per hour. So, if it increases now, say if you have increased it in this form, then this speed will reduce. So, this is the limiting value, and if we go down here, then in that case the speed can increase. So, there the reduction is going to be there, and in this case there is a increase in the speed. So, we can identify based on the condition being given in a numerical that what needs to be done. Now, let us come to another numerical here. Here a locomotive is given with a driving wheel load as 20 tons, and there are 4 pairs of driving wheels. They are carrying a train load of 1200 tons on a broad gauge track. The speed of the train on a track with gradient being given as 1 in 150 is 50 kilometers per hour, and the coefficient of friction is 0.23. We have to calculate the curvature that the train can traverse. So, it means now there is an impact in terms of the curvature as well as gradient as well as the other resistances which will be there in the initial conditions due to rolling stock as well as due to atmosphere. So, we have small w as 20, n as 4, capital W as 1200, G as 1 in 150, F as 0.23, and capital V as 50 kilometers per hour. So, this is the data which is given to you. So, you can first of all write down those data and then it starts working with the same concept that the hauling power has to be greater than or at least equals to the resistances being offered by the track. So, calculating the haul power of the locomotive as N into W into F, what we get is there are 4 pairs each having a load of 20 tons, with F being given as 0.23. So, it is 4 into 20 into 0.23 will give you 18.4 tons. So, this is the power which with the locomotive is going to move, and this is the total resistance also which can be taken up by this locomotive to carry the load of 1200 tons forward. Now, here the resistances which we are going to talk about, because there is a gradient as well as a curvature, and we are talking about a broad gauge. So, it is due to friction, due to wave action, due to wind, due to gradient and due to curve. So, initial ones are 0.0016 W, then 0.00008 W into V plus 0.0000006 into W into V square, plus the gradient effect, that is W into tan theta or W into G, plus the effect of the curvature for a broad gauge track, which is defined by this coefficient as 0.0004 into W into dr, that is the degree of curvature. Now, this degree of curvature is to be found out, and rest of the values have been given to us. So, W is being given as 1200, here in this equation it has been taken out. V is given as 50 kilometers per hour, and the gradient has been given as 1 in 150. So, if we put all these values here, so what we get as an equation is 16.52 plus 0.48 dr, and this 16.52 plus 0.48 dr, it is being correlated with the hauling power which is available as 18.4 tons. Now, if we correlate these two, 18.4 tons as well as the resistance being offered here, then what comes out to be, the dr comes out to be 3.92 degrees. So, roughly it is a 4-degree curve. So, a 4-degree curve with a gradient of 1 in 150, that will sustain a speed of 50 kilometers per hour for a load of 1200 tons. Subjective, the locomotive have 4 pairs with each axle having a axle load of 20 tons. Now, here is another numerical. Consider this data of weight of locomotive is given as 130 tons. So, we can say this is W1. The weight of loaded wagons is 48 tons. So, say this is W2. The number of wagons attached to the locomotive is 18. So, say this is and 2. Tractive effort of the locomotive is being given as 19.2 tons. The rolling resistance of the locomotive is defined as 3 kgs per tons. That means, whatever the total load is there, with respect to that we have to find out. Then rolling resistance of wagons is 2.5 kgs per tons. So, here the load can be calculated for the wagons, and then we can find out what is the resistance which is being offered by those 18 wagons. And the speed of the train is given as 60 kilometers per hour. So, what we have to calculate? We have to calculate the gradient which this train assembly can negotiate. So, first of all, the rolling resistance of the wagon we have to find out. So, rolling resistance of the wagon is 18 into 48 into 2.5. Now, what is this value? 18 into 48 into 2.5. Let us go back. 18 is the numbers, 48 is the weight of one wagon. So, 18 into 48 into 2.5 is the rolling resistance of the wagon. So, the total load is 18 into 48 multiplied by 2.5. The 2.5 is tons per kg per tons. So, it is kg per tons. When we use it here, what we get is 2.16 tons or 2160 kgs. Similarly, if we talk about locomotive, in the case of locomotive, what is being given? So, it is 3 into 130. Now, why it is 3 into 130? 130 is the W1 being given for a locomotive, and this 3 comes from here the rolling resistance of the locomotive, 3 kg per tons. So, 130 into 3 gives you 390 kgs or 0.39 tons. So, this is the another value. Now, total resistance is going to be how much? 2.16 plus 0.39, that is 2.59 tons is the total rolling resistance. So, this is how we have calculated, and instead of the formula which otherwise we could have used as 0.0016 or 0.00008 or 0.6 times 0 into 6 into those values. Now, total weight of the train will be how much? Total weight of the train is the weight of the locomotive plus weight of the wagons, 18 wagons, with each wagon is having a weight of 48. So, we get 994 as total weight W. So, total trail resistance is the rolling resistance, with resistance dependent on speed, resistance due to wind and resistance due to gradient. The rolling resistance we have calculated. So, we have that value with us. Then for the rest of the things we are putting the value. So, it is 0.00008 into the weight which we have calculated and the speed being given. Here it is 0.0000006, then weight and the speed square, then weight into g percent, because this is what we have to find out. So, when we solve it, what we get here is 9.46824 plus 994 g, that is the resistance which is there, and that has to be equated with the tractive effort, and the tractive effort has been given directly as 19.2 tons. So, if we use this 19.2 tons along with this, what we get G G comes out to be 0.97905% or it is 1 in 102. So, the maximum gradient which can be there in this case is 1 in 102. Another numerical has been taken up here. It says the resistance to the gradient together with curve resistance. So, there is a resistance R due to the gradient and there is a resistance due to the curve, and that curve for 3 degrees is equal to the resistance. So, that is the total resistance, this one, this is equals to the resistance which is offered by a gradient of 1 in 150. So, there is a gradient, this is 150. So, this is the condition being already stipulated in this numerical. What we have to calculate, that what is this gradient G. So, the resistance due to gradient and curvature is W into G plus 0.0004 into W into dr, because it is being given as a broad gauge track. So, as per condition, W into G plus 0.0004 into W into dr is nothing plus W into G1, where this G1 is related as 1 in 150, which is given to you here. So, we put these values and W goes out because this is a common factor. So, we are left with G plus 0.00004 into dr, this is equals to 1 by 150, dr is given as 3 degrees. So, we put that value there. So, we will get a value as 0.00667 minus 0.0004 into 3, that is a degree of a curve being given, and finally, the gradient which is possible in this case is 1 in 183, which is obvious that this has to be less than 1 in 150 with which it has been equated, because in this case of 1 in 183 a curve resistance is also being added. Now, come to the another numerical. Here we have to calculate the maximum permissible load that a broad gauge locomotive with 3 pairs of driving wheels bearing an axle load of 22 tons each can pull on a straight level track at a speed of 80 kilometers per hour. So, this is the very first thing. Here we can break it here. So, this is one part. Then the second part, it says also calculate the reduction in speed if the train has to run on a rising gradient of 1 in 200. So, this is another part. And the third one, it says what would be the further reduction in speed if the train has to negotiate a 4-degree curve on the rising gradient, and the coefficient of friction has been given as 0.20. So, let us look at this. The first thing is we have to calculate the maximum permissible load, then we have to calculate the speed given the gradient is there, and then again we have to calculate the speed given gradient as well as the curvature is there, and this is more or less similar to what we have done in the probably the first or the second numerical. So, the hauling power of the locomotive is N into W into F. So, N is 3, W is 22, F is 0.2. So, what we get is 13.2 tons as the hauling power. Total resistance on a straight track is a simpler one related to friction, wave action, and wind effect as an atmospheric condition. So, 0.0016 W, 0.00008 W into V, 0.000006 into W into V square. So, that is what a formula which we will be considering here. So, when we put the values here, we do not know what is the value of W, and this is to be calculated. So, W remains as such, but V is given as 80 is being placed there. So, we get an equation here as 0.01184 W. And this is being equated with the hauling capacity of 13.2, that gives us a load of 1115 tons. Now, in this case, the total resistance with the gradient effect, if we add that, so the three things are going to remain the same, only this W into G is being added, or previously we have written it as W as tan theta. So, one and the same thing. So, if we use this and we have to calculate the speed, so V is not known, but the load is there. So, load which we have calculated previously, which will come into this particular equation along with the effect of the gradient. And this equation, when it is being equated with the hauling capacity which we calculated previously as 13.2 tons, and then solve this equation for the value of V, because it is a quadratic equation in V, what we get is 48.13 kilometers per hour. Initially it was moving at a speed of 80 kilometers per hour, and because we have provided a gradient, so that gradient has made an impact here. So it has reduced the speed by 31.87 kilometers per hour. And further it says that there is also a curvature, and for that particular curvature the effect will come in terms of 0.0004 into W into dr, where dr is the 4 degrees curvature being given and W already we have calculated as 1115 tons. So, if we put all of these values again along with the gradient and create this equation for the resistances and then solve it for V, what we get is 43.68 kilometers per hour. So, previously it reduced to 48.13, now it has reduced to 43.68. So, there is a reduction further of 4.45 kilometers per hour. So, these are the some of the type of numericals which can be there, which you can look at and try to solve by yourself. Make a habit of solving again all of these numericals which have been discussed with you. With this we close this lecture. What we have discussed today is the different conditions which are related with the hauling capacity and the resistances which can be offered to a train and a locomotive. So, these are all being discussed in terms of a numericals, and we have calculated either W or V or G or dr and solve all of these things. So, we close here. Thank you. We will be meeting in the next lecture.